Computer Science Principles, Unit 1 Review. This is part of a review for your Unit 1 summative assessment. In addition to this review, you should be doing the practice work assigned during the unit, go back over your notes, and do the practice test. In this unit, which was an introduction to computer science, you should be able to summarize the key points in the historical development of modern computers, be able to understand and write algorithms for everyday tasks. You should be able to identify the various hardware and software components of a computer, and you should be able to explain the role of computer languages in computer science. Now, what is computer science? Well, a misconception is that computer science is the study of computers. Computer science is no more about computers than astronomy is about telescopes, biology is about microscopes, or chemistry is about beakers and test tubes. Science is not about the tools. It is about how we use them and what we find out when we do. A second misconception is that computer science is the study of how to write computer programs. While programming is extremely important to the discipline, like the computer itself, programming is a tool. The construction of a high-quality program is important, but the methods it embodies, the services it provides, and the results it produces are also important. Misconception 3. Computer science is the study of the uses and applications of computers and software. A wide range of people use computer software, but it is the computer scientist who is responsible for specifying, designing, building, and testing these software packages, as well as the computer systems on which they run. Okay, here are some first dates in computer science. You could go about, you could go about taking a look at these and figuring out from the internet what they are, or we can just go through them here. In the 1930s, we had early theoretical work on the logical foundations of computer science. The 1940s, first general-purpose electronic computers existed. And, oh, by the way, if you look up the definition of a computer in a dictionary in the 1930s and 1940s, you will find that it is a person who computes. Now, in 1951, the very first commercial machine, the UNIVAC-1, came into being. By 1957, we had the first high-level programming language, which was Fortran. Many engineers, as well as computer scientists, programmed in Fortran, which was a procedural language. 1962, the first Department of Computer Science was established at Purdue University. They were Boilermakers. That's their mascot, by the way. 1969, the creation of the ARPANET, the first working model of the internet between 4 universities on the West Coast, was developed. 1971, the very first email is sent. 1971, the first email. Now, IBM launches the PC, and the first personal computer comes into being in 1981. Now, understand, this first personal computer was extremely expensive, so most people did not necessarily have a personal computer, okay? It was a while before they were prolific among homes. 1990, the first website becomes live. Amazon was launched in 1995. 1997, the machine beats the chess champion Garry Kasparov. In 1998, Google was founded. And in 2004, Facebook was founded. Now, in computer science, we talk about the algorithm. The central concept in computer science is the algorithm. Computer scientists study the behavior of algorithms to determine if they are correct and efficient. Just because something's correct, if it takes 100 years to do, people just aren't going to use it. Design and build computer systems that are able to execute algorithms, design programming languages, and translate algorithms into these languages so they can be executed by the hardware. And then they identify important programs and design correct and efficient software packages to solve these problems. Informally, an algorithm is an ordered sequence of instructions that is guaranteed to solve a specific problem. Step 1, do something. Step 2, do something. Step 3, do something. On and on and on. Step N, stop, you're finished. An algorithm can be as specific as you need it to be. The key with algorithms is providing enough level of detail so the reader can carry out the instructions, but not so vague that they cannot do it successfully. Recall the video that we watched in class about the peanut butter and jelly sandwich. Well, here's an example of instructions for making a peanut butter and jelly sandwich. Take out 2 pieces of bread, a knife, a jar of peanut butter, and a jar of jelly. Take them out where? Put knife in peanut butter and put enough of it on the knife. What is enough? How much do you want? Spread the peanut butter on the bread. Should it be in or out of the jar? Is this the peanut butter that's on the knife or in the jar? Repeat steps 2 and 3 with the jelly. Same questions. And then put the pieces together. And oh, by the way, what is a piece? Do you tear off a piece or is a slice a piece? Well, we had issues. Remember the poor little boy? He got so frustrated with Dad. Okay? Issues. You had to assume that the user knew how to use a knife. You had to assume the user would be able to open up the peanut butter and jelly lids, and that you assumed that they knew to do that. You had to assume the user knew how to spread. And you needed to know what a piece of bread is and how much was enough. How specific do you need to get with your instructions? Well, it all depends on who's reading it and who's going to follow them. The instructions given to a 7-year-old for a PB&J would probably be a bit different than the instructions a 30-year-old would read. This is the same thing for the computer. There are things we can assume that when you tell the computer to do it, it will know how to do it without further instruction. Other items, you will have to be more explicit in your algorithms. All operations used to construct algorithms belong to one of only 3 categories. First, sequential operations. These are operations that carry out a single, well-defined task. When that task is finished, the algorithm moves on to the next operation. Sequential operations usually are expressed as declarative statements, such as put the knife in the peanut butter. Then we have conditional operations. These are the question-asking instructions of an algorithm. And conditionals, you got a yes or a no, true or false. They ask a question and the next operation is then selected on the basis of that answer. If there is not enough peanut butter on your knife, put your knife into the peanut butter again. If statements. Number 3, iterative operations. These are the looping instructions of an algorithm. They tell us not to go on to the next instruction, but to go back and repeat the execution of a previous block. So something like repeat moving the knife back and forth on the slice of bread until the bread is covered in peanut butter. That's a repetitive or iterative operation. You do the same thing over and over. Adding numbers algorithm. Add the 2 rightmost digits. So I've got 45 plus 39. So that means 5 plus 9 equals 14. If that is greater than or equal to 10, write the ones place digit of the sum and set the carry variable equal to the tens place digit for the answer. Number 3, so we've got carry is equal to 1. Now, if that number is less than 10, write the digit and the carry variable is equal to 0. So there you've got that conditional. Then next you're going to add the next 2 most right digits plus the carry value. Repeat 2 and 3 until there are no more place values and your carry value is 0. And here are the steps. An algorithm, step by step. Now, in addition to learning about algorithms and the basics there, we've talked about hardware, software, and languages. Hardware, the structure and organization of virtually all modern computational devices, are based on a single theoretical model called the von Neumann architecture. You probably don't need to remember this particular name, but it's good to know that it is the von Neumann architecture. It's named after the mathematician who proposed it in 1946. It is based on the following three characteristics. Four major subsystems called memory, input-output, the arithmetic logic unit, and the control unit. That is something you do need to be familiar with. The ALU and the control unit are often bundled together and are generally called the central processing unit, or the CPU. It's the brains of the operation. The stored program concept is having the instructions to be executed by the computer represented as binary values, and those are stored in memory, right down here. The sequential execution of instructions in which one instruction at a time is fetched from memory and passed to the control unit where it is decoded and executed. And of course, you have input and output. Not every program has input and output. Some just take input and do something, others just produce output. Now, memory is the functional unit of a computer that stores and retrieves instructions and data. There are two main types. First, we have volatile memory. This information disappears when the power is turned off. This is what we call random access, or RAM memory. In the RAM, there are fixed cells, each with an address where information is stored. Non-volatile memory, when you press any save feature on your computer, it is stored in the non-volatile memory. This can be the auxiliary memory on your hard drive, your USB device, or cloud storage. The input, output, or I/O units are the devices that allow a computer system to communicate with and interact with the outside world, as well as store information for the long term. So input devices, and by the way, these are not exhaustive lists. We have a keyboard, mouse, microphone. Output devices, screen, speaker, printer. Okay, all different kinds of things can be input and output. Here are some hardware examples. Okay, you can pause the video, take a look at them. They are in the notes packet that goes with this video. Now, the ALU is the subsystem that performs mathematical and logical operations such as addition, subtraction, and comparison for equality. This, along with the control unit, make up the CPU. The CPU does the computing, the processing, and the bulk of the work for a computer. The CPU works closely with the main memory. As it is working through processes, it's storing information in the main memory and then reading it and restoring it. And the ALU, along with this, modifying it. This is really your brains. The stored program is a sequence of machine language instructions stored as binary values in memory. It is the task of the control unit to fetch from memory the next instruction to be executed, decoded, and executed by issuing the appropriate command to the ALU memory or I/O controllers. Now, we have the hardware, physical, touch it. The software. Well, the software, we first have system software. This is a collection of computer programs that manage the resources of a computer and facilitates access to those resources. System software often acts as an intermediary between the users and the hardware. The set of services and resources created by the software and seen by the users called a virtual machine, or VM. Okay, some ideas like that are your operating system, different utilities, print utilities, things like that. Application software allows the user to address some very specialized tasks of interest to the user. For example, writing a document, creating an image, browsing the web, doing calculations in some kind of a spreadsheet, playing a game. Those are all applications. And the applications sit on top of the system software, which communicates with the hardware. Now, how do we write programs? Well, with computer languages. Algorithms are a precise sequence of instructions for processes that can be executed by a computer and are implemented using programming languages. In class, we've seen examples of algorithms using human language. Human language, however, is riddled with ambiguities and assumptions that computers cannot handle. Remember the peanut butter and jelly sandwich. Writing down even a small set of creating instructions is nearly impossible unless we can agree on certain language constructs ahead of time and how these will be implemented. I saw bats. Does it mean you're cutting a bat in half? Does it mean you saw the animal bat and you saw multiple animal bats? Does it mean you saw multiple wooden bats? Or are you cutting an animal in half? Now, examples. If student's grade is greater than or equal to 60, print passed, else print failed. Set total to 0, set grade counter to 1. While grade counter is less than or equal to 10, input next grade. Add the grade into the total. Set the class average to the total divided by 10. Print the class average. While these provide a great way to write and develop algorithms, the computer cannot understand this language. This is all in English. The next step from designing your algorithm, writing it in pseudocode, is to develop a language that has no ambiguity. This is a programming language. Each action must have a precise, unambiguous meaning attached to it. All programming languages are derived from a human need to concisely give instructions to a machine. A machine can't guess at what you mean. It can't interpret it. It doesn't understand innuendo. It's got to be specific and repeatable. Now, all programming languages have their pros and cons with their functionality. Different branches of industry prefer their own specific type of language. Here are a bunch of different languages. Once upon a time, I don't see Pascal in here anymore. Pascal was originally the language of AP Computer Science A, and then we went to C++, and now we're with Java. I personally have programmed in assembly language, Perl, MATLAB, SQL, Visual Basic, SQL, JavaScript, Visual Basic, C++, Python, and Java. Yes. And here are companies and the ones that prefer different things. For the most part, Java is probably the #1 language in use. Now, how does a computer read a programming language? Well, a computer at its very basic level only communicates in binary. Binary is a sequence of ones and zeros. Actually, it's electrical impulses, on or off, which are communicated with these switches that are on or off. We will learn more about binary in the next unit, but for the purpose of this unit, know that for a computer to function, we have to translate our programming language in machine language, which is the language designed for a specific machine. Machine language is written in binary and is complicated, if not impossible to understand. Way back when computers first were built, you had to know how to do this. Now, no one cares, no one codes in binary, and it represents the most basic level of abstraction. Know that computers communicate in binary, but we ignore the details of how. We just trust it works whenever we use computers to communicate. After computers were created to communicate in binary, the next step was to develop a language that was closer to our human language. That is, when assembly language was born. Assembly language is designed for people as well as machine. This first appeared in the early 1950s to help create a more productive, user-oriented environment. Assembly language is still extremely difficult and tedious to program in. Now, both of these, machine and assembly language, are what we call low-level programming languages. They work closely with the computer, and even though assembly language was a step closer to human language, it is still not great to code in. You literally, over here, are storing things or setting a bit or storing something in a particular register. What we really were excited about in programming was when we got high-level programming languages. High-level programming languages such as C++, Python, Java, etc. are much more user-oriented. They are not machine-specific, and they use both natural language and mathematical notation in their design. A single high-level language instruction is typically translated into many machine language instructions. This goes through a compiler, which creates object code. It's an intermediate code, somewhat like assembly code, that goes to a linker that creates binary or executable code. Again, machine language and assembly, those are low level. C++, Java, Python, those are high level. Pseudocode, English, Spanish, Japanese, those are your natural languages. Someplace between programming languages and our natural languages is pseudocode. A little more specific, but it's still not readable by a machine. Now, OO, or OOP, stands for Object-Oriented Programming. Significant object-oriented programming languages include list order-based is Java, C++, C#, Python, R, PHP, Visual Basic, .NET, JavaScript, Ruby, Perl, Object Pascal, Objective-C, Dart, Swift, and others. Text-based languages require coders to conform and obey formal syntax. When you create a program in a text-based language, a compiler then takes the code and translates it into machine language. Text-based language is much more flexible than what you are able to code. In this class, we will be using JavaScript. Now, visual programming is a type of programming that lets humans describe processes using an illustration. This is not Visual Basic. Visual Basic still uses text. This is also considered block-based programming and is used in programs such as Scratch and Snap. Block-based language involves an interface that allowed computer programs to be built by simply dragging and dropping puzzle blocks to represent complex programming constructs and commands. The most common block-based languages are Scratch and Snap. To get an example of block-based code, you can go to blockly.games maze and have a try. And that concludes your Unit 1 review.